So today we talk about the frequency analysis. So we have already covered that Z transform and discrete signal, discrete system and implementation of discrete systems. So all those things we have already covered. So this week we talk about the frequency domain analysis of the systems and signals, and then we talk about the discrete Fourier transform. Okay. So as you know that Fourier analysis, that continuous time Fourier analysis, you have already studied in mathematics, continuous time Fourier analysis. So what is the basis of that Fourier analysis? The Fourier analysis said that a signal can be decomposed into a sinusoidal component. So any given time domain signal, what Fourier said, can be decomposed or can be divided in a sinusoidal component. So let us say I have a signal, time domain signal, continuous time domain signal xt. This can be decomposed in sinusoidal component. So I am saying the signal xt consists of different sinusoidal components. So that continuous domain Fourier analysis, you have already learned it. Then what is the meaning? What is the physical meaning of that things? It means that if I have a time domain signal, I can decompose the time domain signal in term of sinusoidal signal. I have a signal xt in time domain signal. I can say it consists of 1 Hz frequency, 2 Hz frequency, so 1 Hz sinusoidal, 2 Hz sinusoidal, 3 Hz sinusoidal, 4 Hz sinusoidal, like that. Different sinusoidal component I can take, and I can say that if I take the sum of all sinusoidal component, I will get back the signal xt. So that is the basis of Fourier analysis. So how it is done? If you see that equation of the continuous domain, so it is nothing but a x of k or x of capital X of omega is nothing but a, you see, the integration of minus infinity to infinity x of t then dt. So it into e to the power minus j omega t dt. So why we do that? So as you said that a signal can be decomposed in a different sinusoidal component. So what Fourier does, that we create a sinusoidal component and convolve with the signal. So as a sinusoidal component acts as a filter. So I pass the signal through a filter and get that component. So that is the idea behind that Fourier analysis. So Fourier analysis, why we do that Fourier analysis? Because the Fourier analysis give me a pace, or I can say that it is a transformation pace, where I can see what are the frequency component consist in the signal. That is the Fourier analysis advantage. Then what he said? That even function are composed only on cosine transform. So e to the power minus j omega t. So if I say that e to the power minus j omega t or plus j omega t, it is nothing but a cos omega t minus j sin omega t or plus j sin omega t. So e to the power j, so if you see the Fourier, basis of the Fourier, let's I take a new slides and explain you, because explanation is very much important. Okay. So what I said, what Fourier said, that any signal xt can be, xt is a continuous signal. So xt is a time domain continuous signal, can be decomposed in term of minus infinity to infinity x of t e to the power, let us say, minus j omega t dt. So what is the meaning? Meaning is that I am creating a e to the power minus j omega t signal and convolved with xt. If that signal exists, so I get a component. So it is nothing but a convolution. So as you know, e to the power j omega t has in two parts. If it is minus, then I said cos omega t minus j sin omega t. So cos omega t is the real part j sin omega t is the imaginary part. So I know that the odd function and even function. So if it is a even function are composed of only cosine function and odd function are composed of only sine function. Then what Fourier said? A finite number of frequency component can be used to approximate a signal. So I can say a signal consists of some finite number of sinusoidal component. Frequency component of a periodic signal are harmonically related with discrete spectral line, which is called line spectrum or described by Fourier series. So when I say frequency component of periodic signal are harmonically related with discrete spectral line, e to the power j omega t, let us say it is 1 Hertz component or 2 Hertz component, it is a line spectra. Okay or not? It is a line spectra because with 1 Hertz I get a line or 2 Hertz I get a line. So it is a line spectra and described by a Fourier series. Fourier series can be expressed in exponential form also, and aperiodic signal are decomposed in a non-harmonically related sinusoidal. Resulting spectra is continuous, described by a Fourier transform, and there is an inverse Fourier transform exists. So those are the Fourier transform property, and those we have already learned in mathematics, that Fourier transform of a continuous signal. So what is the basis? Basis is very simple. Any signal can be decomposed in term of sinusoidal signal. So that is the basis of Fourier analysis. Next one, now I have a signal which is discrete. Time domain, it is not xt, it is a discrete x of n capital T, while capital T is the sampling period. So now I have a discrete time Fourier analysis. So I do not have a continuous time. So you know the discrete domain, the integration becomes summation and time becomes time instant. So discrete time Fourier series, so instead of integration it becomes a summation. So it is nothing but a series. Okay. So if it is series, then I can say it is applicable to a periodic digital signal. Discrete Fourier transform applicable to aperiodic digital signal or LTI process. Okay, let us forget about all those things. Let us think about that what is discrete Fourier transform. Discrete time Fourier transform. Discrete time Fourier transform. So what it is meaning? Meaning is that my signals, whether it is system response or whether it is signal, in time domain it is discrete, but in frequency domain it is nothing but x to the power e j omega, it's continuous, omega is continuous. So that's why it is called discrete time Fourier transform, DTFT. So Fourier domain, it is not discrete Fourier transform, I said DTFT, discrete time Fourier transform. Okay. So what is the meaning? So I have a continuous signal xst. I have a continuous signal. Now what I want a transform in discrete signal. So what is discrete signal? So discrete signal is nothing but a x of t has to be, I have taken a time instant which is nothing but a x of nt, or which can be said x of n. So t is replaced by nt, where capital T is the sampling period. So if you see the Fourier transform, what I said, minus infinity to infinity, if it is continuous, if it is discrete, the integration becomes summation, n equal to minus infinity to infinity x of nt e to the power minus j omega t. So omega small t becomes n into capital T, n into t. Okay. So, I can say that if it is discrete time Fourier, discrete time signal, then I said that the Fourier transform, or I can say the x Fourier transform is nothing but a n equal to minus infinity to infinity x of n t into e to the power minus j omega n into t. So, now this is nothing but a x of n. So, I can say let the discrete time Fourier transform of x of n is represented by capital X e to the power j omega. So, I said in Fourier frequency domain x is omega domain, it is continuous. So, that is why I said it is discrete time, but frequency domain it is not discrete. So, you know the continuous frequency is capital omega and this is equal to nothing but a omega. So, this is radian per second and this is radian per sample, that I have already covered in my week number 1 lectures. So, this is radian per second and this is radian per sample. So, discrete time Fourier transform x capital omega is nothing but a x to the power j omega, x of, you can say the x of z also, where z equal to e to the power j omega, n equal to minus infinity to infinity x of n e to the power j omega n, because I do not write the t, t is nothing but a sampling frequency. So, t is constant for everywhere, that is why I said x of n instead of e to the power j omega n t, capital T, I just omitted j omega n, n is the index of the signal. So, this expression is called discrete time Fourier transform. Okay. So, if I want to get back the xn again, so inverse discrete time Fourier transform x of n, you know that why it is 2 pi, why it is minus pi to pi. You know that any discrete signal, the highest rate of oscillation is varies from minus pi to pi. So, it is not infinite, any discrete signal is periodic. So, I can say it is sampling period is the period. So, I can say minus pi to pi, highest rate of oscillation is pi or minus pi. So, that is why it is minus pi to pi. So, total range of variation is 2 pi, that is why it is normalized by 1 by 2 pi minus pi to pi x of e to the power j omega e to the power j omega n d omega. Inverse Fourier transform. Inverse Fourier transform. You know the Fourier transform is minus infinity to infinity x of t e to the power j omega t dt. What is the inverse Fourier transform? Then it is frequency domain integration, integration in frequency domain. So, that is why I said it. Why it is integration not summation? Because in frequency domain this is continuous. Signal is continuous in frequency domain, it is discrete in time domain only. Okay. So, I said then you can see that DTFT is periodic in frequency period of 2 pi because of e to the power j omega pi n. So, let us say I write down e to the power j omega plus 2 pi, which is nothing but e to the power j omega into e to the power j 2 pi. E to the power j 2 pi is nothing but a 1 cos 2 pi plus j sin 2 pi. So, sin 2 pi is 0. So, it is 0, cos 2 pi is nothing but a 1. So, I can say this is equal to 1. So, this is nothing but e to the power j omega. So, I can say that the DTFT is periodic in the frequency of period equal to 2 pi. So, do not confuse continuous Fourier transform, discrete time Fourier transform, then we go for the discrete Fourier transform. So, I have not yet gone to discrete Fourier transform. I said continuous Fourier transform. The example is that I create a continuous signal of sinusoidal, sinusoidal signal, convolved with the original signal, and I get back that whether that component exists or not. So, that is the procedure for calculating continuous Fourier transform. Now I said the signal is in discrete form. So time instant is not continuous. So I got DTFT, discrete time Fourier transform. Again in frequency domain it is continuous. Time domain it is discrete. Frequency domain it is continuous. And I know that if it is discrete Fourier transform, the period is 2 pi because Fs is equal to 2 pi and it is varies from minus pi to pi. Is it clear? So now I go for, let us suppose there is some examples are given, you can calculate x of n equal to del n. So x of e to the power j omega, what should be the formula? N equal to minus infinity to infinity x of n e to the power minus j omega n e to the power minus j omega n. Now it is say n equal to del n, that means it is 1 when n equal to 0, elsewhere it is 0. So I can say that this summation only exists x of 0 e to the power j omega into 0. So it is nothing but a 1. Similarly, if I say x of n equal to del of n minus n0, so I can say x of e to the power j omega is only 1. So this function is only 1 when n equal to n0. So I can say it is nothing but a x of n into n equal to minus infinity to infinity e to the power minus j omega n. So at n equal to n0 only x of n equal to 1. So 1 e to the power minus j omega n0. So e to the power minus j omega n0. Let us x of n equal to un. So what is the formula? Un n equal n greater than equal to 0 only it is 1, elsewhere it is 0. So I can say this summation will vary from 0 to infinity x of n e to the power minus j omega n. So now x of n equal to 1, so e to the power j omega to the power 0, j omega to the, so I can say it is nothing but a 1 by e to the power minus j omega. Again if you see this one is nothing but a shifting, so this is shifted by n sample, so that is why e to the power j omega n will be upside and here will be e to the power j omega. So those are the example of DTFT, discrete time Fourier transform. Signal is in discrete form, but it is in continuous in frequency domain. Clear? Okay. Now I go for a system. Suppose I have a system. I want to find out the frequency analysis of this system. So I have already explained the impulse response. So Hn is the impulse response. So how do we get the impulse response? We know if I excited the systems with a unit impulse, then the output is nothing but the impulse response of the system, because I know H omega or Hn is nothing but output is nothing but a output by input is nothing but a frequency response of the response of the system. So impulse response we get when we excited the system with an impulse, and if I get the output, that output is characterized the impulse response of the system. Now think that instead of impulse, if I excited the system with a e to the power j omega, e to the power j omega n, let us say omega equal to 1 hertz. So 2 pi f, omega is equal to 2 pi f, 2 pi into 1 hertz. Normalized sampling frequency if I said, then if it is 1 hertz, sampling frequency is 8 kilohertz, then it will be 1 by 8 kilohertz. That is the component. This is normalized discrete frequency. So for every normalized discrete frequency, I excited the system. Then I can say the output of the system. So I excited the system with e to the power j omega n. I get the output y of n. I get the output y of n. So that output is nothing but the frequency response of the LTI system. Physically you understand, forget about the mathematics. think about, I have a system which is a black box. I excited the system with a 1 Hz signal, 2 Hz signal, 3 Hz signal, 4 Hz signal, and I calculate the output. So the output is nothing but a response for 1 Hz signal. So e to the power j omega n is nothing but a pure sinusoidal signal. So I excited the system with a sinusoidal signal. So response is nothing but the power of that sinusoidal signal. So basically, I am calculating the response of the system for particular frequency. So I get the frequency response of the system. So e to the power j omega n, as you know, the normalized, so if the signal is in discrete form, then you normalize discrete frequency. What is normalized discrete frequency? You know that this omega is nothing but a 2 pi f by fs. So I excited the system for every normalized discrete frequency. I collected the output, and that output is characterized the frequency response of this LTI system. So that is the physical. Now how do you do the mathematically? Let us say I have a signal x of n. I excited the system with x of n. I get the output y of n, and h of n is the impulse response of the system. Then as you know, the yn output is nothing but a convolution of impulse response of the system and the signal. So it is nothing but a convolution. So as a think about, a system may consist of let us say I have this system has a amplitude at 1 Hz, it has an amplitude 500 Hz, it has an amplitude 560 Hz, it has an amplitude, otherwise it is 0. So when I apply a 1 Hz signal, I get an output, otherwise it is 0. So if I plot the output, I get the frequency response of the system based on the excitation. So mathematically it also has to be true. So this is a convolution. So what I said, the LTI output yn is nothing but a convolution of system impulse response plus input. So what is the input? X of n is equal to e to the power j omega n. So instead of j omega n, I can instead of x of n minus k, I put e to the power j omega n minus k. So which is nothing but a hk e to the power j omega k into e to the power j omega n. So if I say e to the power j omega n outside and take the sum of this one k. So what is this? This is nothing but a frequency response of the system. And what is this? This is nothing but a shifting of different frequency. So frequency response of the system multiplied by the input frequency give me the response of the output. So suppose in the frequency response of my LTI system, that's why I am examining. Let's say I have a 500 Hz component, I have an 1.5 kilohertz component. This is my frequency response of which is nothing but a h of e to the power j omega. Now when I excited the system for every, let's say for every omega, I am exciting. This is I dropped in omega. Let's say I draw in omega scale, normalized discrete frequency. This is omega 1, this is let's say omega 2. So when my input is e to the power j omega 1 n, then I get output. Elsewhere it will be 0 because it is a multiplication of h e to the power j omega to the input. So I get the frequency response of the system. Okay. So that way I can calculate the frequency response of an LTI system. So what is frequency response? So how do I interpret it? So frequency response is nothing but a impulse response e to the power minus j omega k, k equal to minus infinity to infinity. So, I can say this is a complex number, I can say. So, h of e to the power j omega is a complex number. So, let us say complex number is a plus jb. So, every complex number has a two part, one is called amplitude, which is nothing but a mod part, and one is called theta part, which is nothing but a phase part. So, h of e to the power j omega has an amplitude which is mod part, and e to the power j phi omega which is nothing but a phase part. Or I can say h of e to the power j omega has a two component, one is real part, real of it h of e to the power j omega, and another part is because this any complex number has a real part and has an imaginary part. So, I can say h of e to the power j omega has a real part and imaginary part. A plus jb is a complex number, it can be has a real part and has an imaginary part. So, I can say that e to the power j omega, again I can, instead of writing real and imaginary, I can write in cos and sin term, because e to the power j omega k has a minus, I think it is minus, e to the power minus j omega k. So, it is minus j omega k has a two part, one is cos j omega k, cos omega k minus j sin omega k. So, this part is real part which is cosine component, this part is imaginary part which has sine component. So, real part is cosine component and imaginary part is minus sine component. If you see that real part is the even function and imaginary part is the odd function, see that minus. So, even function f of n is equal to f n, then I said it is a even function. F of minus f of n equal f of minus n equal to f n, then I say even function, and f of n is equal to minus f of n, minus f of n, f of minus n is equal to minus f of n is nothing but a odd function, that you have heard it. So, even function and odd function. So, I have a magnitude response also. So, what is the magnitude response? Any complex number a plus b, real part and imaginary part, magnitude response is nothing but a root over of real square plus imaginary square, root over of real part square plus imaginary part square, that is the magnitude response. And the phase response, you know, the phase is nothing but a tan inverse, theta is nothing but a tan inverse real part divided by imaginary part divided by real part, arctag tan inverse real part divided by imaginary part, which is also a function of omega. So, I can plot h e to the power j omega mod of h e to the power j omega, which is called magnitude plot, magnitude response, and this is called phase response. So, now if I say the group delay function, so difference of phase, derivative of the phase response with the different omega is called group delay function. We will describe called linear phase, non-linear, linear phase filter, non-linear phase filter. So, linear phase filter means group delay will be 0. For all signal there will be no phase shift, because what I said, LTI system, I get the frequency response by applying a signal which is a sinusoidal signal. Now, if you see the system change the phase of the, if the different signal, different output of the system is different, for different input is different phase, then I can say arbitrary phase system. But if it is linear phase, that means all the component will come out from the system with the same phase, then we call linear phase response. So, that is determined by the group delay function. Now there is a symmetry and asymmetry. So a mod of h e to the power j omega is a symmetry property. So if for a LTI system with real valued impulse response, the magnitude response, phase response of the real component and the imaginary component possess the symmetry property. So any LTI system frequency response has a symmetry property. So real component is a function of even function omega, period is 2 pi. Imaginary component odd function of omega, period is 2 pi. Then the magnitude response is also an even function, because my mod of e to the power j omega minus j omega also same, mod is same, sign is positive, it is positive. So I can say the magnitude response is an even function, whereas phase response is an odd function, because if it is negative it's become, so tan theta, theta is equal to tan inverse b by a. If it is negative it will be minus tan inverse b by a. So I can say that if it is negative, x of minus f of minus n equal to minus fn, so that's why it is an odd function. Now if it is even function, then I can say it is symmetry over the pi. 0 to pi will be same as pi to 2 pi. So if I know e to the power j omega for 0 to pi, so frequency here omega is normalized discrete frequency, so it varies from 0 to pi. So if I know the system for 0 to pi, I can draw the frequency response of the system. How should we look like this? So this is 0 to pi. Then what should be the pi to 2 pi? 0 to minus pi will be same, because minus pi 0 to pi is the frequency response of the discrete system. So 0 to, if it is symmetry, symmetry over here 0 to pi response and 0 to minus pi response is same. Similarly, at 2 pi also it will come. Then it is coming here 0 to pi, then the negative side. So it is a symmetry property. This is the magnitude response of the LTI, frequency response of an LTI system. Now phi omega is a odd function, so 0 to pi, if it is this side, then I can say 0 to minus pi will be negative side. F of n is equal to minus f of minus n, then I can say it is an even function. So here it is same, but if it is f of n, f of n is equal to f of minus n is equal to minus f of n, then I said it is odd function. Here if you see it is negative, so it is an odd function. But again it will be repeat from pi to 2 pi, 2 pi to 3 pi. So that is the odd function. So if you can take any signal and you take the omega, and if you plot the omega value with respect to omega, plot the phase value and the magnitude response, you get this kind of response. So this omega is normalized discrete frequency. So normalized discrete frequency is nothing but a f2 pi f by fs. So again I am summarizing the normalized discrete frequency. Let us say this one. So normalized discrete frequency is nothing but a e to the power kt. So n or nt, whatever you can say, the t is divided into k into multiply by t. So I can say omega is normalized discrete to 2 pi f by fs, which I have already covered in my first lecture. So you know that f by fs. So f by fs, what is the maximum? So what is the maximum baseband signal? Okay, forget about that part. So suppose I have a signal, let us say, given an example, forget about, I have a signal of, let us say 100 kilohertz signal. Okay, let's say I have sampled it as 200 kilohertz. So you know that if Fs is equal to 200, forget about 100 kilohertz, let's say Fs is equal to 200 kilohertz, then you know what is the baseband signal, highest frequency component of the signal is Fs by 2. So F is equal to Fs by 2. So I can say omega is equal to twice pi Fs by 2 divided by Fs. So I can say it is nothing but a pi. So maximum normalized discrete frequency is pi. If it is minus pi also, if it is minus f, it is minus pi. So minus pi to pi is the maximum frequency content of the signal. Okay, what is the period? It is nothing but a 2 pi. After every 2 pi, signal will repeat itself. Okay, so normalized discrete frequency. So f by 2 is equal to 50 kilohertz. So f1 is equal to 50 kilohertz equal to pi. So if f1 equal to 20 kilohertz and sampling frequency is 100 kilohertz, I can say it is nothing but a 20. Let's say pi is 50 kilohertz. So I can say how many pi will be there. Or I can do directly f by f. Let's say Fs is equal to 8 kilohertz. Let's say 8 kilohertz, and my baseband signal f1 is equal to 2 kilohertz. Then I know normalized discrete frequency omega is equal to 2 pi f1 by fs, which is nothing but a 2 pi f1 is 2 divided by 8. Kilo cancel. So I can say 2 pi into 1 by 4 is equal to pi by 2. Pi by 2 or yes, pi by 2 is the normalized discrete frequency. So this you can explore a lot when we design filter, when we calculate the frequency response, when we plot, we'll do this kind of thing. So you convert the normalized discrete frequency to the again normal frequency or frequency to normalized discrete frequency. So those things we will do. So omega is in normalized discrete frequency. So this is the frequency response of a system. This again I am saying that this is called discrete time Fourier transform. Time domain signal is discrete, but frequency domain signal is continuous. So that's why I said h of e to the power j omega, where the omega is normalized discrete normalized frequency. Okay? Okay. So next class I will talk about DFT, discrete Fourier transform. Okay? Thank you.